All right, recording is started. It's 1:15, so we'll start for today. Well, good afternoon, everyone. Let me put the screen back to chapter 4. Okay, so today we're going to talk about section 4.2. Which last class we kind of talked about, well, what does it mean if the first derivative is equal to 0? Today we're going to sort of explore what it means for the second derivative to be equal to 0. Okay, so just kind of moving on in that direction. But before we do that, we need to finish up a little bit of things I left hanging from section 4.1. So that's what we're going to do first. Let's see. In terms of announcements, there's going to be a quiz today. You also have a homework assignment due today. So the quiz today is over sections 3.3, 3.4, and 4.1. And the next assessment is going to be the second exam on March 29th. So that's 12 days from now. It's on a Tuesday, I think. So we got this weekend, then next week, then next weekend, and the following Tuesday will be our second exam. So in that direction, I will post, as promised, I'll post a practice exam, which is not a carbon copy of the actual exam, but it will give you a sampling of some problems with most of the concepts that we have learned since exam 1. And I will also post a list of things you should know or know how to do. Okay, in addition to that, there's going to be a review on Thursday before the exam in class. But also, I'll be reviewing constantly during office hours today, this coming Tuesday, this coming Thursday, and there will also be SI sessions throughout next week. And Daria, do you have any special plans for the week of the exam?
It's on Tuesday, right?
The exam's on Tuesday, yeah. So.
I can schedule a review session for Monday before.
Okay, so Monday you think you might do a 2-hour instead of a 1 hour?
Yes. I don't know the time and location yet, but I'll let you know once they approve it.
Okay, so most likely there will be some kind of extended SI session the day before the exam as well. So that's another great way to review for that exam. Any questions about administrative aspects of the course before we start today's lesson? Yeah, Seb.
What's everything that's going to be covered on this exam? Like what chapter?
Okay, so this exam is going to cover loosely chapter, the second exam covered up to, I think, midway through chapter 2. So chapters basically 2 through 4. But probably a focus on 3 and 4. That said, there's definitely material from chapter 1, which if you don't know how to do it, then it will make things difficult on the exam, just because it's sort of baked in, I guess, to some of the problems. Does that answer your question? Yeah, so the focus will be on chapters 3 and 4. Any other questions? Okay, then let's start for today by first going backwards and reviewing what we learned in the first section of chapter 4, which there was really kind of a lot of information in this section. So, we started off with this observation that when we see functions attaining minimums and maximums, we noticed that oftentimes the derivative will be 0, or the slope of the tangent line will be 0 when we hit one of those minimums or one of those maximums, right? So that was the observation that we made, and we sort of fleshed out this theory of how to find minimums and maximums of functions based on that observation. And the observation was, well, when we see a minimum, we see that the derivative is 0, but not necessarily the other way around, right? If I see that the derivative is 0, it could be a minimum, or it could be a maximum, right? Or it could be one of those neither situations, right? It could be something like this. Would also have a derivative equal to 0. So, but since I know that every minimum will will occur at a critical point, that is, then I can just find all the critical points and test them one by one to find where the local minimums are or the local maximums, okay? So that process was done by first collecting the critical points. So let me remind you of the definition of a critical point. We say that any point x equals p, why don't I just go down to this? No. Okay, we said that any point p which satisfies f prime of p is equal to 0, or f prime of p doesn't exist, okay, then that is going to be a critical point. Okay? And the way we learned how to test whether critical points were minimums or maximums was by using this notion of the first derivative test, okay? Which said, loosely speaking, let's say I have a critical point. I look at what is the first derivative doing a little bit to the left and a little bit to the right. And if I observe the behavior that the function is increasing before my critical point and then it's decreasing after the critical point, then I might surmise that my function reached a local maximum at that critical point. Okay, so this is just the basic idea that if I'm riding on a roller coaster and I'm facing up like this, and then 2 seconds later I'm facing down like this, then at some point in the middle I reach the top of the roller coaster, right? Or vice versa for the minimum. Okay, so we had basically 3 scenarios. If the derivative is 0, one of three things is going to happen. Either the derivative switches from being positive to being negative, or the derivative is going to switch from being negative to being positive, and then the final scenario is that the derivative isn't going to change sign. Okay? So these corresponded to the 3 behaviors which we see, namely the local maximum, the local minimum, and neither behavior, quote unquote. Okay, so let's pause and let me ask the. Sorry, what? Oh. Oh, you mean outside? Yeah, I think they were shooting a flamethrower out there like a minute ago. So I don't know. That seems like it's still going on, I guess. Okay, so yeah, sorry about the noise, I guess. Nothing we can do about that. Okay, so let me ask, are there any questions just about the basic principles behind the first derivative test? Yes?
Will the critical points always be maximum or minimum points, or can they fall anywhere in the middle at times?
So the question is, will critical points always be maximums or minimums? Is that what your question is? Well, here we can see actually, we found that this function had a critical point at x equals 0, and this corresponded to neither a minimum nor a maximum, right? Because although the derivative is 0 at this point, let me show you with the I don't even know what to call this, the laser. Okay, so we have this point here where we see that actually the tangent line will be 0 at this point, right? Or the tangent line's slope will be 0, right? But just because the derivative becomes 0 at this point doesn't mean that we have a minimum or a maximum, because it happens that the derivative kind of bottoms out. It's negative, 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 and then it's to 0, but then it starts becoming negative again, okay? So that's a situation where we have a critical point that doesn't correspond to a maximum or a minimum. Great question. Are there any other questions about the basic principles behind this first derivative test? Okay, then I'm going to move on and talk about a different kind of a test that you can use to check what's going on here. So I think what I'm going to need to do is erase. I'm going to erase this drawing that I've done here because I need to use the graph for the second part. So if you're on your own, maybe just, or if you're writing on your paper, how would I want you to do this? I guess what I would say is maybe try to copy this picture over to the side, maybe. In fact, maybe that's what I'm going to do. I'm going to leave all this here, and I'm going to copy the picture. Probably should have done this before class. Okay, so what does it do? It comes up, and then it goes like that, and then it comes through. Comes up, hits the maximum, and then it sort of goes through 0 like that, and then down again, and then it hits a minimum. Okay, and here's 1, 0, and -1. Okay, so, in fact, why don't I just copy this all the way down to the relevant section. Okay, so we're going to talk about problem number 8, or section 8, I guess, where we're going to look back at this graph and we're going to observe the behavior near these critical points, not of the first derivative, but of the second derivative. We're going to ask ourselves what is happening to the second derivative when we are close to each of these points. So let's check what is the concavity of the function to the left and to the right of the point that we are interested in. So let me add a page so that I can paste that and we can observe what's happening. Okay, so if I take a look at this first critical point and I observe, okay, a little bit to the left, it looks like my second derivative is what? Positive or negative? Positive? Why do we think it's negative or positive? What does the second derivative tell us about the shape of our graph? Yeah, whether it's concave up or concave down. So if it's concave up, then the second derivative is positive, and if it's concave down, then the second derivative is negative. So this shape kind of looks like an N, right? So I think concave down, right? It's curving downwards, and so that tells me that the second derivative is negative. And also a little bit to the right, it looks still like f double prime is still negative to me. All right, then let's take a look at this other point here. Here it looks like, well, a little bit to the left, this looks like f double prime larger than 0. And a little bit to the right, this kind of looks like f double prime less than 0. Okay, concave up and then concave down. Okay, and then let's look at the bottom down here. It looks like to the left and to the right, we have f double prime larger than 0 in both cases. Okay, so these are our observations about what is happening with the second derivative here. And it is going to help us to identify whether a critical point corresponds to a local maximum or a local minimum in the following way. if I have a critical point here, and I notice that the second derivative nearby is negative, then the function is concave down. If the function is concave down, then this point must be a maximum. Okay, this is the logic that we're going to use. So, in other words, if I'm riding on my roller coaster and the coaster is bending downwards like this, and I reach a extremal height, either a minimum or a maximum, but if it's bending like this, there's no way it could be a minimum. That's the basic principle here. And the idea behind what we call the second derivative test. Okay, so we've classified already that the point at x equals 1 is a local, x equals negative 1 is a local maximum. And what I see here is f double prime of negative 1 is less than 0. Okay, the second derivative has a uniform sign nearby negative 1. Okay, and then the other point at 0, I think I did that one in red, was a neither situation. And what we had was f double prime of 0 was equal to 0. F double prime a little bit left of 0 was positive. And then f double prime a little bit right of 0 was negative. So this is a situation where we see, okay, when we have a neither situation, it turns out that for this neither, we ended up with a second derivative that didn't even have a sign at that point. Okay, let's check another one. So the one at 1, which I think I did with purple, was a local minimum, right? Did I circle the right one for the first one? Yeah, okay. Local minimum, and we noticed that f double prime of 1 was larger than 0, right? It was bending upwards. Okay, so based on our observations in problem 8, we are coming up with a method for classifying critical points of a function f as local maximums, minimums, or neither if you only have a formula for the second derivative f double prime. And the way it's going to work is as follows. So let's say x equals p is a critical point of f of x, meaning that if I take the derivative of f and I plug in p, I either get 0 or it doesn't exist. So p is a critical point of f of x, then if f double prime of p is larger than 0, p corresponds, how about x equals p, corresponds to a local, let's see, f double prime larger than 0. That means we're bending like a U shape, which means we're going to get a minimum. Okay? So the corresponding picture for this one is we're concave up, which means our picture looks like this. Okay? Second option, f double prime of p is less than 0. Then guess what we're going to get? X equals p corresponds to a local maximum. Okay, so the picture looks like this, right? We're concave down. Okay, now one pitfall that I have seen some students fall into is that it's a little bit confusing that the second derivative is positive, and so positivity makes us think like, okay, big number, makes us think maximum. But actually, if we have the second derivative is positive, what it means is that the function is concave up, which means that the actual function is reaching a minimum. Okay, so it's a little bit wonky here, and it feels kind of strange that larger than 0 for the second derivative gives us a minimum for the function. And likewise, less than 0 for the second derivative gives us a maximum for the function. Okay, so that's one pitfall to be aware of. And the final step is, what if f double prime of p is going to be equal to 0? And this one's a funny one, because it doesn't necessarily mean that p is not a max or a min. If f double prime of p is equal to 0, the test fails. We gain no information. So you might say, hang on, well, if I have f double prime of p equals 0, the question says I'm supposed to classify all the critical points, but f double prime of p equals 0, I know that that means that I don't know what's happening at that critical point. And this is a situation where you'd be absolutely correct. You need to go back and use the first derivative test if you run into a situation like this, which happens actually with relative frequency. For example, if you have a function like f of x equals x to the fourth, okay, this looks like a parabola that's slightly more like that. And we can clearly see that 0 is a minimum. But if you take the second derivative of this guy, you're going to get 12x squared, which if you plug in f double prime of 0, you're going to get 0. And so if you were to use the second derivative test, you would say, well, this tells me nothing about what's happening at x equals to 0. But we know from knowing what the graph of a quartic function like this looks like, that there is going to be a minimum there. So that's a situation where we have to use the first derivative test. Okay. Any questions about the second derivative test so far before we see an example? Yeah, Brendan.
So if you find the second derivative of a function and you get a positive, I guess if you find that the answer is positive, then it does not necessarily mean it'll be positive. It depends on whether the graph is pointing up, like if the curve is pointing in an M shape or a U shape. That will determine like whether it's positive or negative, right?
Yeah, I think you've summarized it well. So the basic summary is that, yes, the second derivative, remember, the second derivative isn't going to tell us anything about how high up or down our original function is. The only thing the second derivative tells us about our original function is which way is it bending. Okay? And I know that if I have a critical point and the second derivative tells me that I'm bending downwards, as in this first point at x equals -1, then that's telling me that there's going to be a maximum at that point based on how it's bending. So yes, I believe you summarized it succinctly. Okay, any other questions? All right, if not, then let's see an example. So what I want to do here is I've pre-written some notes, and I'm going to go through the first part a little bit more quickly. So I don't think that you need to write all of this down. I don't want you to write all of this down, but I will put this on the blackboard so that you can see it when you're doing like your homework or something like that. So this is a description, okay, of, let's say I have a function and I want to find and classify the critical points, okay? Which, by the way, is an almost guaranteed problem on the exam. There will almost certainly be a problem which says, here's a function, find and classify all of the critical points as local maximums or local minimums or neither, okay? That's almost a freebie to show up on the exam. So let's say I have this function, f of x equals x cubed over 3. I'm gonna write all of this out in generality, but in each of these parentheses I write, okay, what am I actually gonna do with this specific function, okay? All right, so the first step to finding and classifying the critical points of the function f is to find the critical points, right? Then I can worry about classifying them later. The way I find them is through a two-step process. I take the derivative of that function. Okay, so for the function which I've written in parentheses here, I would get the derivative would be x squared minus 1. And the second step is to find all of the points x equals p such that if I plug them in to the derivative, I either get doesn't exist or f prime of p is equal to 0. Okay? And one sort of crucial qualifier here is that these points should all be in the domain of f of x. Okay, so what does that mean? I should only search for critical points x equals p which are in the domain of f of x. So if f of x is a function and there's a point which is not in its domain, so let's say, for example, if f of x equals 1 over x, the domain of this function is x should not be 0. So in particular, when I take the derivative of this guy and I get negative 1 over x squared, okay, then x equals 0 is not a critical point. Of f, even though if I plug it into the derivative, I get 0. Because the original function, 0 is not in the domain. So I need to look for points x equals p which are in the domain of f and cause one of these two things to happen. Okay, so once I have these critical points, okay, which let's just do it really quickly for our function. So our function was x cubed over 3 minus x. I took its derivative and I said what? I said, well, x squared minus 1 exists for all x, which are real numbers. So since my original function was a polynomial, I know I don't need to worry about f prime not existing. So I'm only going to check where is the derivative equal to 0. So I solve p squared minus 1 equals 0. That's the derivative where I plug in p. And I found out that the critical points are going to be either 1 or minus 1. So now I have the critical points. I found the critical points, and I'm ready to move on to the second part of the problem, which is to classify them as minimums or maximums. Okay. So how do I do that? Step 3 is to classify the critical points using the first or the second derivative test. Okay, so two possible methods that we can use here. And which one you use is really up to you. The only thing we need to be slightly mindful of is that if we use the second derivative test, it's possible that it doesn't work and we have to go back and use the first derivative test. So the first derivative test will always work for this process. The second derivative test sometimes is a little bit easier if you have the foresight when you start the problem that you think that's going to be easier. And I'll explain how you can see that in a little bit. Okay, so let's walk through how the first derivative test works. Okay, so remember, I have my function f of x was x cubed over 3 plus x, and its derivative, f prime of x, was x squared plus minus 1. This should have been a minus here. Minus 1. Okay. Excuse me. Okay, so the first step of the first derivative test is to plot the critical points on the number line. So in this case, negative 1 and 1 were my critical points. Now I know that negative 1 and 1 are the two places where the derivative is equal to 0. So I know that in between negative 1 and 1, the derivative has a uniform sign, by which I mean it's either positive or negative. Okay, and likewise, to the left of negative 1, the derivative is either positive or negative in this region. It's either positive or negative in this region, and it's either positive or negative in this region. So what we're going to do is check the sign of the first derivative in each subinterval by just checking what is the sign of the derivative at a given test point inside each subinterval. And the way that I choose the test points from each interval is the test point has to be fully inside of the interval, okay? It doesn't necessarily have to be halfway between the 2 points or whatever, but it should be fully inside. And I like to choose points which are nice. So I like to choose 0 here instead of like, I don't know, 0.159, because it's going to be easier to plug in 0 into the first derivative, which is what I need to now do. Okay, so I'm going to take each one of these test points and I'm going to plug in to the first derivative. Okay, so remember, the first derivative was x squared minus 1. So I'm going to take each of the test points which I chose from the 3 subintervals, and I'm going to plug it into the first derivative and see if I get something which is bigger than 0 or something which is less than 0. So when I plug in -2, I get something larger than 0. Okay, so at this point up here, we see that the first derivative is positive. And that tells us that the first derivative is positive in this entire region. And then it hits 0 at -1, and then let's see what happens. Well, in the second interval, I know that it has a single sign, so I just check what is the sign of f prime of 0. Well, if I plug in 0, I get -1, which is something negative. So I know that the derivative is positive in this region, and then it's negative in this region. And then, as we can see from the bottom calculation, again, it becomes positive in the third interval. So this tells me what is the behavior of the first derivative in each of these subintervals. Now remember, whether the first derivative is positive or negative tells me something important about the original function. Can anyone tell me what I learn about the original function if I know the sign of the first derivative? That's right, whether the function itself is increasing or decreasing. So now I like to draw these little lines here which kind of remind me of what's happening. So because the first derivative is positive in this region, I draw a line which is going up to denote that the function itself is increasing. And then likewise for f prime of 0 being less than 0, I draw a line going down to signify that in this region, the original function is decreasing. And then finally, the original function is increasing in this last region. And this is enough for me to decide whether or not -1 or 1 correspond to local maximums or minimums. Because what does this say? This says that before I get to -1, my function's going up. And then right after I hit -1, I'm going down. So I can say with confidence that I reached a local maximum at x equals -1. Okay, this is a lot of information all at once, so let me pause. Are there questions about what we've done so far? Yeah.
I'm still a little bit confused on how you found the critical points. That was further up. I understand the bottom part there, the plot and the number line, but whenever you took the derivative of the function and then how did you know what to plug in to find the critical points?
Sure. So I know that I will have a critical point, okay, at an x value if when I plug it into the derivative, I get 0, or it doesn't exist, right? Of course, I didn't need to worry about doesn't exist for this problem. So I just did the following. I took the derivative of this function, and I want to find the values p such that when I plug them in, I get 0. So I plug in p into this function, and I get p squared minus 1. And I want to find the numbers such that if I plug them into that equation, I get 0. So I set it equal to 0 on the right-hand side. And from here, solving p squared minus 1 equals 0, this is a quadratic equation. So we can solve it using the quadratic formula, or as I did it, using factoring. So that was how I found p equals 1 and p equals -1 to be our critical points. Good question.
How would you do it if the point did not exist?
Maybe I'll show an example of that another day. I'll prepare one for you. How about that?
Would you ever do that on like a quiz or an exam?
I think it would be a... I think it might be a little bit rude to do that on a quiz or an exam. Maybe on a homework. We'll see. Okay. You know, if it's a situation like that, then it will be. I would make it as easy as possible, I think, because that's a complex kind of scenario. All right. Any other questions so far? Yeah, Brendan.
So you essentially, for the first derivative test, you took the original function, found its values, you found where it equals 0 or where it does not exist, and then based on those values, you plot them on the number line, and then you plot nearby points to determine whether the function increases or decreases within the subintervals.
Exactly.
Okay.
Yep, you got it. Okay. So I know that at any point on the number line where f prime switches from positive to negative, I'm going to get a local max, okay? And if f prime switches from negative to positive, I'm going to get a local minimum, okay? All right, so this is the first derivative test. Let's see how the second derivative test works. So suppose I didn't want to do all of that number line crap, and I just want to use the second derivative test. Now, the second derivative test tells me, let me return to this graph. It tells me that if at a critical point my function's concave down, then it's a max. So as long as I can say, well, is the function concave down at the critical point or is it concave up at the critical point, then I can say, well, it's either a maximum or a minimum. So here's how the second derivative test works. So again, I need to find the critical points. So once I have the critical points in hand, my goal here is to take the second derivative and plug them in. See what I get? So if I take the second derivative, okay, I get 2x here. So this is coming from the fact that, recall that f of f prime of x was x squared plus 1. So I take its derivative. That tells me what f double prime is. So x squared plus 1, its derivative is 2x. And now I'm just going to plug in the critical points. So when I plug in negative 1 into 2x, I get negative 2. If I plug in 1 into 2x, I get 2. So since the second derivative test gave me numbers which are both larger than 0 and less than 0 respectively, I know that the test worked, and I can say whether these correspond to local maxes or minimums. So the key here is to recognize, well, if the second derivative is negative, then the function is concave down. And if the function's concave down, I must have reached a maximum. If the second derivative is positive, then the function is concave up, and therefore I must have reached a minimum. Okay, so this essentially is a repeat of the conditions, right? It says, okay, if the second derivative is positive, the function's concave up, and therefore we get a local minimum. If the second derivative is less than 0, then the function is concave down, and therefore we get a local maximum. And the crucial thing to remember about the second derivative test is if we get 0, we don't learn anything, and we need to go back and do the first derivative test. So in this case, I think it's a lot less work to, basically for the second derivative test, this was all I did. I just took the second derivative and I plugged in, and it was that easy. So the second derivative test is sometimes a lot simpler than using the first derivative test. But it comes with the caveat that it doesn't always work. Okay, so these are the two ways in which we can classify critical points. And this is like what I would say is your handy guide, okay, for finding and classifying critical points. So when you're doing the homework and you have problems like that, I'd come back to this section and just remember these steps. I've got them numbered, 1, 2, 3, okay? First, find the derivative. Second, set the derivative equal to 0 and find where it either is equal to 0 or doesn't exist. And lastly, we want to classify the critical points using either the first derivative test or the second derivative test. The reason I put the first derivative test on the left is because it's always going to work. But if you do the second derivative test, sometimes it's a little bit easier, but it has the shortcoming that sometimes it doesn't work. So I'd recommend keeping this next to you as you do the homework and practice this process a few times because it's almost certainly going to show up on the exam. All right, any questions about finding and classifying critical points? Yeah, Gino.
So the classifying part is just saying if it's negative or positive?
Well, the classifying part is to say, okay, I have these critical points. We want to say, is that critical point a max or a min or neither?
Yeah.
Okay, so to do that, we can use one of the two tests, which the second test is, I think what you're referring to, says, well, if the second derivative is positive or negative, that tells us whether the critical point is a maximum or a minimum. Okay, yeah, good question. Any other questions? All right, cool. Then I'm going to move on now, and let me make sure I have enough time to do this fully. I think I do. I'm going to talk about something else, which I'm only going to comment on sort of briefly. So section 4.2, okay, we have some more extrema problems. So extrema is, by the way, a word which means maxes and mins. Okay, maxes and mins. Do I need a I guess I don't need that. That would be a possessive, right? Maxes and mins. I don't know. Wow, why don't I just put an E there? Maxes. There we go. Maxes and mins. All right. So that's what finding extrema means. And the second section in chapter 4 is really about a concept which we refer to as inflection points. Oh, low battery. We better plug that in. Hang on a sec. Okay, so essentially what inflection points are is a classification of when does the graph change concavity. We have established what it means for the first derivative to change sign, okay? If the sign of the first derivative goes from positive to negative, we see that we get one of these maximums, right? And if the first derivative goes from being negative to being positive, then that's when we see one of these minimums, right? But the next question has to do with what happens when the second derivative goes from being positive to being negative. Okay? And this is what we refer to as an inflection point. Okay? This is what we refer to as an inflection point. Okay. So, yeah, you're excused, of course.
Can I take that to quiz like
Yeah, no problem. Okay, so this inflection point is where we see the concavity change from being concave down to concave up, or the reverse, right? Concave up to being concave down. And the way it kind of looks on the graph is you just look for one of these points where it's like, okay, we were bending this way, and then after we hit that point, we started to bend the other way. That's basically what an inflection point is. So let me just really quickly scroll down here to this definition here, which is really the entire meat of this section. So if at x equals p we have f double prime of 0 of p is equal to 0, then x equals p is a candidate for an inflection point. Okay, so finding inflection points is much the same as finding minimums and maximums. We start by checking the places where we see that the concavity is 0. And we know that might be a place where the concavity switches from being positive to being negative. So if f double prime is equal to 0, then x equals p is going to be a candidate for an inflection point. How do we check? To verify, check that f double prime changes sign at x equals p. Using the number line method. Okay, so we will see an example of this really quickly, of how do we actually find an inflection point. So let's find any inflection points of the function f of x equals x cubed. And oftentimes on these problems you'll see a caveat. They'll say if any exist. Okay, because it's possible for a function to not have inflection points. Okay? A function that doesn't have any inflection points means that it's either entirely concave up for its entire life or it's entirely concave down for its entire life. Okay, but we know roughly from this graph of x cubed, which we have seen many times, I think we can be confident that there is going to be an inflection point. When we look at the graph here, it kind of looks like we're concave down for a while, and then we hit 0, and then suddenly we're concave up. So that's a good indication that we have an inflection point at x equals 0. So this is where we're going, but let's do it mathematically here. Or how about analytically? So we want to find the inflection points of x cubed. I know that if f double prime of p is equal to 0, then p is a candidate. For an inflection point. So what I'm going to do is start by solving. I'll take the second derivative of this guy and set it equal to 0 and see if there are any points p where the concavity is 0. So I start by getting f prime of x. That's pretty simple to do. It's just 3x squared. And then if I take the second derivative, then I'm going to get 2 times 3x to the 1, which would be 6x. So I'm going to try to find any points p such that if I plug them in to 6x, I get 0. Well, there's exactly one number that I can plug into this spot that will give me 0, and that's 0. So now I have verified p equals 0 is a candidate. Now, to check whether p equals 0 is an inflection point, I'll use my number line here. And I'm going to pick test points. Say -1 and 1. To the left of 0 and to the right of 0. And what I need to check is that f double prime changes sign from left to right. So I should see that f double prime goes from being negative to being positive, or it goes from being positive to being negative. This is what I need to check. So I plug -1 and 1 into the second derivative. When I do f double prime of -1, I get 6 times -1, which is -6, which is less than 0. So I know that in this region I'm concave down. In the second region, I check a test point from the second region, which is f double prime of 1. And I can see that that will give me 6 times 1, which is 6, which is larger than 0. So in this region, I'm concave up. So, on the left, the second derivative is negative, meaning that the function is concave down. On the right, the second derivative is positive, meaning that the function is concave up. Okay? With these things in mind, I can conclude f double prime changes sign at x equals 0. Therefore, x equals 0 is an inflection point. Or I could say 0, 0 is an inflection point. Both of these statements are okay. Okay, so this has a cadence which is very similar to the first derivative test. Okay, only when we're looking for inflection points, this has to do with the second derivative. So when we make our number line, instead of plugging things into the first derivative to check whether the function is going up or going down or what's happening with that, we're checking whether the function is concave down and then concave up. If we switch from concave down to concave up, this means that we've had a change in concavity, which is what the definition of an inflection point is. Okay, it's a point at which we change concavity. Any questions about second derivative? Yeah, Brendan.
So the same would apply for a parabolic function, right? There would be an inflection point at 0, 0 because it's changing.
Well, not for x squared. For x squared, its second derivative would be 2. So that function is concave up everywhere. So no inflection points. But for example, let's see an example of a situation where we can have a candidate which doesn't pan out to be an inflection point. So let's repeat this exercise. Let's find any inflection points of the function. Instead of x cubed, we're going to do the function f of x equals x to the 4th power. Well, I know that if I have an inflection point, it will occur at a location where the second derivative is 0. So first I find the first derivative. That's going to be 4x cubed. Easy. The second derivative is going to be 12x squared. So all I need to do is find the points where this second derivative will be equal to 0. So I solve 12p squared equals 0. That tells me that p must be what? I square something, multiply by 12, and I get 0. What do I start with? 0, right? Okay, so p equals 0 is a candidate for an inflection point. So what do? I make my number line. I put on 0. And all I need to do is check a test point to the left, maybe -1, and a test point to the right, maybe 1. And let's see what happens. If I do f double prime of -1, I get 12 times -1 squared, which is 12, which is larger than 0. So I'm concave up in this region. And if I plug in f double prime of 1, I get 12 times 1 squared, which is just 12, which is again larger than 0. So even though the concavity flattens out at x equals to 0, I notice that I'm actually concave up in both of these two regions. And that's because if you look at the graph of x to the 4th, I mean, my graph isn't going to be that good. But essentially what it does is it looks kind of like a parabola, but it sort of flattens out when you get to 0, and then it goes up. So it's one of those weird situations where we're concave up to the left, we're concave up to the right, but right when we actually hit this point, our graph is perfectly flat in the sense that it has no curvature at this point for a fleeting moment. Yeah, Christian.
So what if we were like doing one of these and we found that there was no inflection point at 0, whatever your first candidate would be, and like say there's a chance that there's an inflection point somewhere else. So like do you just keep testing stuff, or do you just kind of...
Well, you need to test all of the points such that if you plug them into the second derivative, you get 0. So that could be multiple points. In this case, there was only one value for which this second derivative would be 0. So that was the only one I needed to check. But once I've found all the candidates. So I go one by one through each of the candidates, and I say, is this candidate an inflection point? Yes or no. Is this candidate an inflection point? Yes or no. And I do it all using this number line. So in particular, I might have more spots on my number line here. Does that answer your question?
Yeah.
So for this problem, the question is find any inflection points of f of x equals x to the 4th, if any exist. And my answer to it would be, there are no inflection points for this function. Okay. Any other questions? Okay, then we'll stop there for today. So please clear your desk. We're going to do the quiz. And if you have a smart device of some kind, like an Apple Watch, please put it away. If you have a cell phone, if you don't mind, put it in your book bag. You can use a scientific calculator for this, but I don't think it will help. For now, just please keep this on your desk face down until everyone has a quiz. Okay, does everyone have a quiz? Okay, you may begin.